Hi, my name is Kay. I'm a junior in math.
Hi, I'm Tyler. I'm a sophomore in mathematics and computer science.
Hello, I'm Andrew. I'm a freshman in math and computer science.
And this is our project, Theorem Proving in Lean. This is run through the Illinois Geometry Lab in the math department under Professor Philip Iranimi. We started this project last fall.
So first of all, what is Lean? Lean's it's a theorem prover and a programming language, which allows us to create definitions, prove theorems, and perform mathematical computations, all in a kind of interactive manner. And it lets us formally verify mathematical statements. So for years now, mathematicians have been building a library in Lean, which formalizes definitions and theorems from all areas of math, called MathLab, which is available to view at this link. Now in Lean, instead of set theory, it uses type theory, and in type theory, each expression has an associated type. So for instance, we write little a is a type of big A instead of little a is a member of the set big A. And we can build new types from existing ones. For example, if alpha and beta are types, then we can use this to denote that the types of functions, or use this to denote a new type of functions from alpha to beta. So our main goal in using Lean is to formalize ideas in first order logic and model theory. For example, languages and structures, terms, formulas and sentences, models, Vought's theorem, and definability and omenability. And so now I'll, Andrew, take a look at some of the progress we've made so far.
All right, so first off, we have what is called the notion of a language. So a language, which we can call L, is essentially a set of symbols that stand for functions, relations, and constants. Each function or relation has an associated arity. So it's essentially just a natural number that tells us how many arguments these symbols are going to require. One important thing to note is that none of these symbols carry, I guess, like meaning right now. These are only, the language just helps us define what symbols we're specifically going to be using. So a more concrete example of a language in Lean is the language that has the symbol, I guess, which we can call multiplication, which is a binary function, and then a constant, which we can denote by the Arabic numeral 1. So in Lean, we have a function R that returns the empty type, because in this definition of our language, we have no relations. F is going to return the type with one element when it gives input 2, because we have a single binary relation, and then C returns the type with one element because we have a single constant. So moving on, as I previously said, these symbols don't actually have, I guess, meaning until we give it an interpretation on a structure. So an L structure is a set M that's paired with an interpretation of each symbol from a language L. For the purposes of Lean, we also have the assumption that this set is inhabited, so essentially that this set is non-empty. This is an example of our definition of a structure in Lean. So as you can see, each of the functions in our language L now has interpretation, same thing with the relations and constants. And we also have a universe, which denotes the set that this structure is acting on.
Okay, next we have terms. We based our definition off of David Marker's definition in his book Model Theory, in which a constant is a term, a variable is a term, and if we have an n-ary function and we apply it to n terms, we get another term. Our definition differs from this in the sense that to work with recursion in Lean, we had to introduce the notion of a leveled term. So we started the same way, where we said constants and variables are terms of level 0. And then we introduced the notion of an n-level term for an n-ary function. And then we made our definition such that if you apply a level 0 term to a level n term, you get a level n minus 1 term. And so that way, once you apply n level 0 terms to an n-ary function, you'll get another level 0 term. And so in this definition, a level 0 term is equivalent to a regular L term in the standard definition.
Okay, next up, we have the concept of a formula. And I guess the motivation behind a formula is to sort of model basic mathematical logical statements. So the definition for a formula can be done inductively. We're starting off the symbols standing for always true and always false. So top and bottom are formulas by default. And then if we have two formulas, then connecting them with the logical connectors and or simply sending not to a formula are also defined as formulas. If we have a formula and a variable, then applying the quantifiers there exist, and for all are also formulas. And then finally, for any relation in this language with an arity n, and we have n L terms, applying the relation on these n terms is also a formula. So you can see, because of this inductive definition, we can implement this in Lean in a pretty straightforward manner. Next up is the notion of a sentence. So in order to sort of formalize what a sentence is, we first need to discuss what it means for a variable to be free or bound. So a variable is free in a formula if it is not quantified. So for a variable to be quantified, it must be preceded by one of the quantifiers there exists or for all. So if this does happen, the variable is bound. And we define a sentence as a formula that does not contain any free variables. So in terms of implementing this in Lean, determine whether or not a formula is a sentence depends on whether or not depends on what variables appear in the formula. And so we define some helper functions to help us extract a list of the variables that appear in a formula, and then determine whether or not a given formula actually is variable free. And so using these functions, the definitions in Lean come pretty straightforward.
Okay, next we define the notion of models. If we let L be a language, M be an L structure, alpha be a variable assignment from X to M, and phi be an L formula with free variables from X, then we have M models phi under alpha if the interpretation of terms and formulas under M and alpha yield a true statement. So our definition is inductive again, and we take a language and a structure over that language. And if we take a variable assignment and a formula, we will get either true or false, depending on if it is modeled or not. And so we start with the base cases for any variable assignment and for any structure. The always true formula is going to be modeled. The always false formula is not going to be modeled. And then these atomic formulas, which are the relations applied to terms, are dependent on the term interpretation and the interpretation of the relation under the structure. And then the rest follow inductively based on the logical connectives and quantifiers. Next, we proved Vaught's theorem, and to do so, we introduced a result of the Löwenheim-Skolem theorem as an axiom. Löwenheim-Skolem asserts that for a theory over language L, if that theory has an infinite model, then it has a model for any infinite cardinality greater than or equal to L. This is a theorem in model theory, although it is extremely difficult to prove in Lean, so we introduced it as an axiom. We then formalized the proof of Vaught's theorem in Lean, which is the theorem that says that if a theory is k-categorical and has an infinite model, it is complete. We included the full proof of this just to show that, so in the book, the proof of this theorem is 5 or 6 lines, and it took us a lot more than that, simply because it is sometimes very difficult to convince Lean that something is true, even though if you are writing math like by hand, it's very easy. And that's because Lean is an interactive theorem prover, and you have to convince it that everything you're doing is correct. As far as other topics, there are a lot of smaller topics, smaller definitions, and smaller lemmas that we have proven in pursuit of formulas, sentences, models, Lowenheim's golem, and Bott's theorem, such as isomorphisms, embeddings, elementary equivalence, theories, variable assignments, term interpretation, etc. But those took a lot of work, but their purpose was to get us to more fundamental definitions. More important and broad topics that we considered working on included the formalization of the notion of a Gödel encoding and the formalization of the proof of the compactness theorem. Each of these topics, when we wrote out the statement of the theorem in Lean, we realized that it would take a lot of definitions and lemmas, and it would not be feasible to do this in our time frame. Okay, finally, the next steps in this project will entail formalizing the notion of definability of sets, formalizing quantifier elimination in the theory of a dense linear order, and both of these will lead us towards our larger goal of formalizing O minimality. These are our references, and we would like to thank the IGL, Professor Hiranimi, and the grad students on our project for helping us. Thank you.